extremely important. So take it seriously. Now I put that there for you to help you if you want to plot the points. I just want you to find the lengths of segments. And we're going to see if we can kind of generalize how to do it when they're in points of a vertical segment or a horizontal segment. Just find those lengths. I'll give you a couple minutes for that. All right, guys. We're back. Okay, so you could plot the 2 points, 2, 3, and 2, 9, right? You'd have 2, 3, and 2, 9. There we go. I didn't feel like putting it on there. What would the length of that segment be from 2, 3 to 2, 9? 6, right? Oh, we're getting 6? All right, nice. Now, did you count boxes? You did the distance formula. I saw that. I was like, whoa. Some people are saying I just did 9 minus 3, right? It's a little easier. Okay. Second one, we have the point 1, negative 2. Oh, let's say that's right here. Again, you could put it on there, but then you have another point with the same x coordinate, 1, 5. That would be up here, right? 1, 5, 1, negative 2. What would the length of that segment be? 7. Nice. And so, again, wow, you could just take 5 minus negative 2. Ready? You don't have to use distance formula. If you're trying to find the length of a vertical strip, and you had to just tell a friend, maybe next period, how you do it, what would you tell them? How do you find the length of it? If you know the endpoints of a vertical segment, how do you get the length of the vertical segment? Subtract the y coordinates. Which one do you have to start with? The greater one, the one on top, right? So as long as you take the y coordinate on top and subtract the y coordinate on the bottom, you'll get the length of that segment. Same thing here. It doesn't matter if the one on the bottom is negative. When you subtract the negatives, just add. Y top minus y bottom. Cool. Now, where do we go? No, I didn't want to switch. No. I don't know. Just trying to. Oh no, now I'm in B. Did I close it? No. I closed it. Where do you see it? No, that's this. No, I closed it. Oh, an error. All right, send somebody a message about that. I got to open it again. Ooh, sorry, people. Okay, you don't want to. Okay, we're back. Woo! Okay, you have the point 1, 1 right here, and you have the point 5, 1 over here. 1 and 5, 1, and you want the length of that horizontal segment. They have the same y, so it'll be a horizontal segment. What is it? First of all, 4, right? That length would be 4. Let's do the next one. Oh, I can't see. You have the point negative 2, 3, and then you have the point 6, 3. You want the length of that horizontal segment. What is it? It's 8. Okay. So, again, you got to tell somebody, how do you find the length of a horizontal segment? You subtract the x's. Which one do you got to start with? The greater one, where is it going to be on the page? On the right. All right, let's summarize this. Yeah, the lives don't matter, right? About 1 and 2. Wait, so yes? Numbers 1 and 2, they had the same x coordinate and different y's, right? So that if you connected them, it would be a vertical segment. So we took the y coordinate on top and we subtracted the y coordinate on the bottom. Oh, I'm afraid to go change pages now. Oh, it's gone now what we did. But yeah, here they have the same x coordinate. So when you connect them, you've got a vertical strip. No, they have the same x coordinate. Okay, we just take whatever the y is up here and subtract the y coordinate down there. That's how we got 6. Well, go ahead and plot them on the grid if it helps you. Yeah? Okay. So, in general, if you want to find a vertical distance, like 1 and 2, what do? Okay, we got to subtract the y's. Which one do we start with? Top. So it's y top minus the y coordinate on the bottom. That's how you find the length of a vertical segment. Now, if you've got a horizontal segment and you got to find its length, you don't use the y coordinates. They're going to be the same. How do you do it? Y left, x. You take the x coordinate of the point on the right, and you subtract the x coordinate of the point on the left. It's so important that you really get that. So if you don't get that, go home tonight and plot points and just until you see it. Because that's really going to be, I'm going to use that over and over again this week. And next week. Okay. Oh, now we can go back to the other one. Let's look at that homework. Now, in example C, we started it in class. We said, okay, so here's a polynomial cubic. We don't want to just take the definite integral from -1 to 2, because that gives me the area above minus the area below. And in this problem, we wanted the area above plus the area below. Right? So we had two options. Well, we know if we want the area of this region, you just take the definite integral because it's positive. So whenever the graph is above the x-axis and you want the area between the graph and the x-axis, just take the definite integral. It'll give you the area. So if you take the definite integral from -1 to 0 of this function, that'll give you the area of the first region. But you want to add to it the area of this region here. You have two options. Either you can just put a minus sign in front of the integral wherever the function is negative. So if the graph is negative, make the definite integral negative if what you want is the area. Wherever the graph is below the x-axis, that means negative. Or, I think we liked addition in here, right? You could just keep it addition, but then switch the limits of integration. And that'll get you the area of the second region. Now, on the calculator, you don't have to break it up like that. If you want the total enclosed area between a graph and the x-axis, you just take the antiderivative of the absolute value of the function. And if you did it with the calculator, you just integrate from -1 to 2, but you got to take the definite integral of the absolute value. The absolute value will make it all positive, so you'll get the total area. So if you put it into the calculator, math 9, absolute value of the function, comma x, comma -1, comma 2. Just go from the first 0 to the last. And that gets straight. But if you can't use a calculator, you got to do that. You got to break it up. Now, the answer came out to be 37/12. I have it with the minus. If you have the plus, just make sure your 2 is down here and your 0 is up there. First thing you got to do is take the antiderivative of the function. So you have to take the antiderivative of the function, and then you plug in upper, lower, and subtract. So you want to make sure your antiderivative is good. And then each one of these is going to give you the area of each region. So when you work it all out, the first region has an area of 5/12, and the second region has an area of 8/3. And you add them together, and you get the total enclosed area. Good stuff, right? All right, that was a 3.0 or whatever. Questions on that one? Okay, it's so easy to make a little mistake. Then you got to D. I'm just going to go B's, here. Okay, so in D, it wasn't completely factored and it wasn't multiplied out. You had a lot of work to do. So the first thing you had to do in D was get an idea what the graph looked like. Most importantly, if you want the area between a graph and the x-axis, you have to know where it crosses the x-axis. So you had to get the zeros first. And some people are saying it was really hard to factor. Well, it was partially factored for you. You just had to factor each factor. So you have these 4 factors. And the factors give you the zeros. So it crosses at 0, 2, -3, and 3. And we know because the leading term would be x to the 4th, it goes up to the right. So it has this kind of W shape. So you want to see if you have the right shape. Now, if you want to just use the calculator to get the total area enclosed, you could just put in your calculator as math 9, the absolute value of the function from -3 to 3. You don't have to break it up. You just go from the first 0 to the last 0, and that'll get you the total area enclosed. But if you want to do it without the calculator, you need to have 3 separate integrals, which are going to get you the areas of the 3 regions, and then you'll add them up like that. So now by hand, this is kind of a nightmare. The big thing, though, that I want you to understand is that the first region and this last region, the y's are negative there. So either for this first one or the last one, either keep it positive and switch the limits of integration, or put a negative in front like I have here. So you got to do one or the other. Okay. Now, I don't have like a nice copy of this. Can I even blow this up? The regions, though, let me tell you what the areas turned out to be. The first region turned out to be 729 over 10. Yeah. The second region had an area of 104 over 10. And the last region had an area of 23 over 10. So if you're looking at your answer, like for each integral, what you got, maybe you can find maybe one of them you got right. But here is the big thing that I saw when I was going around. A lot of people forgot, oh, wow, I got to take the antiderivative. Or if they did take the antiderivative, they didn't multiply it out first. Before you can take the antiderivative, you got to multiply it all out. A lot of people wrote minus 18x here instead of plus 18x, the last term. But then you got to take the antiderivative, plug in the upper and lower, and subtract for each one of these. You'll have 3 separate integrals to get the areas of the 3 regions. So it was a bit of work. And I won't spend too much time on that, but just, make sure you multiply it out right and make sure you take the antiderivative right. But yeah, if you plug in one value and you get something wrong, it could mess up the whole thing. So, yeah, it was. But it's so rewarding when you can, even if you got like one of the regions right. I know. I have to go back. What else if you had the wrong sign at one term? You're not going to get any of them right like that. Oh, you know what, guys? Yesterday. Oh, yeah, and then we have to talk about Z, though, also. Where am I here? Oh, yeah, E. E, unfortunately, I didn't realize this little 2 here. Oh, got stuck there. It's not supposed to be there. It's supposed to be the definite integral from negative, this is example E, -2 to 2 of 1 over x. So, does anyone know what that graph looks like? 1 over x? 1 over x. Ooh, that was, well, your one side, so that's 1 over x squared, what you were just doing. 1 over x, it's an inverse variation. Yeah, that's what it looks like, definitely. But yeah, it kind of slid down there. I don't know what happened. But this is what the problem was supposed to say. Go ahead and use your calculator to find this definite integral. Okay. And if you put, yeah, it doesn't work. Do you remember what it said? You know, to divide by 0. Sometimes the calculator will say total not met. And I just wanted you to be aware, in case it ever happens to you again, what's going on when you see that. Think about finding the definite integral of this graph from -2 to 2. All right? So You're just trying to find the area under this graph, and then, what's going on here at 0? You got a vertical asymptote. So when you're trying to find the value of a definite integral and you got a vertical asymptote in there, sometimes it just doesn't exist. It's going off to infinity, right? So just if you see that, realize it just doesn't exist. There, see that again. That was just, and I know yesterday that we did this, and I got all the way to the bottom, and the bell rang, and I just wanted to make sure on yesterday's that we had this. Oh, that's on the next page. So I had this little graph here. I think we filled it all out, but the very last line, it said break it up. So remember, when you break it up, you have two choices. Have a look at that graph, though. If you want the total enclosed area, you can take the definite integral from A to C where it's positive, all right? That'll get you the area of the first region. And what could you do to get the second region? Because there's two different ways to do it. Yes. Plus. Well, yeah, I have to use this, that move. Normally we would say C to B, so we'll do B to C. So either you can switch the limits, B to C, of where the graph is negative, where the graph is below the x-axis, and that'll get you the total enclosed area. So wherever the graph falls below the x-axis, just switch the limits of integration, and that'll get you the actual area instead of a negative number. Or instead of adding and switching the limits of integration where that function's negative, what else could I do? Leave it and put a minus in front, subtract it. So you could take the definite integral from A to C of f of x to get that area of that first region, and then just subtract the definite integral from C to B to get the area of the second region. Got it? You choose. I'll let you decide. But just don't do both. All right, so that would be it. All right, now we're going to have some fun today. Get ready to think that math is the coolest class of your day. Yeah, they already thought that. That's what they said. They really did say that. All right, between curves. Why is this thing just getting bigger and bigger? Oh boy, this. I don't know. Something's weird. Okay. This is actually really neat. The reason I made you go through that do now is because we're going to find the area between two different graphs by adding up, ready for this, an infinite number of infinitely thin rectangles. And our rectangles are either going to be vertical or horizontal. Now, the height, if we use vertical strips, and that's what we're going to do today, I call them strips or rectangles, to get the height of it, we're just going to take whatever y is on top and subtract whatever y is on the bottom. And the width of each strip, see, these are supposed to be infinitely thin, but then you guys wouldn't see it, so it wouldn't be good to put on the boards, so I had to give it a little width. But the width is an infinitely small change in x, dx. So the area of each one of our rectangles, if we use vertical rectangles, will be the height, y top minus y bottom, times the width, dx. Tomorrow we'll use horizontal strips. So we'll go the other way. No! Away. Okay, so here's the idea. If we want to get the area between these two graphs, these two functions, what we can do is sum up the areas of rectangles, these vertical rectangles. Now, I'm not going to draw them all because there's an infinite number of them. Starting here all the way to there, each one of these rectangles or strips has a height of y top minus y bottom, or in this case, y top is f of x, y bottom is g of x. So it'll be f of x minus g of x for the height. Each one will have a width of dx, and we'll be able to sum them up with an integral. That's what the integral is going to be able to do. Starting at x equals a, and go adding them all the way up until x equals b. And that'll get us the exact area enclosed by two different curves. We're summing up an infinite number of rectangles, the areas of an infinite number of rectangles starting at A and going to B. Each rectangle has a height of y top minus y bottom times its width dx. Cool? Let's do it. You just got to see it. You just got to see it. All right. Tell me what the graph of y equals negative x squared plus 4 looks like. A frown, right? There's that parabola. Tell me what the graph y equals negative 5 looks like. Horizontal line. Thanks for saying horizontal. That was nice. All right, this goes up to 4, doesn't matter. So negative 5. So all the points whose y coordinate is negative 5. There we go. We are going to find the area enclosed by this parabola and that line. Even though it's not necessary, I do like to color in this region. So I just have to do that. This is so cool. Wait, where did it go? Before there were more colors. Wait, maybe there's more here. No. There's too many more choices. This one? Oh, no, I just did that. This one? Oh. Oh, wait, I don't want line color, though. Is it? Oh, maybe it is line color. Oh, pick a color in here, guys. Pink? Okay, I'll do pink. I have not done pink today. I'm not really in the mood for pink, but it's all right. It's fine. Okay. Yep. Move. Sorry. I know, I heard you arguing about that the other day. This is lovely. I really was not going to go for the pink, but now I see it. It works. Sometimes you have to put it on to see it. You got to see it on. Lovely. Okay. Now, it does, right? The colors are always better on here than here. Okay, guys, draw anywhere you want. You can't draw in an infinite number of strips. You'd be here forever. So just draw in one somewhere, draw on a vertical strip, just to get an idea what one of them looks like. Yeah. Sometimes you can use either, but sometimes if you use horizontal, it'll take you 2 integrals to get the area, or vice versa. So usually there's a smarter way. I always try to use vertical strips first, but I'll show you actually. I probably won't get to it. It's on, I have an example on the last page of today's notes why sometimes it would be better to use horizontal strips. You can get away with 1 integral instead of 2. So area is the sum of the heights times width. Now to get the height of a vertical strip, how do we do it? We take the general y top minus the y on the bottom. That'll give us the height. And what is the width always going to be if it's a vertical strip? Yes, nice. Now, let's fill in. Make sure when you're looking at the graphs, you always look in the region. If you're in here, what is the y coordinate on top equal? It's not the same number all the time. It's not going to be a number. It's going to be a function. Negative x squared plus 4. That's what the y on the upper function equals. So right top. And then we want to subtract y bottom. What does y bottom always equal? Negative 5. That one's always negative 5, no matter where you draw the strip. That's why you get a number. Minus negative 5. Okay. We can clean that up, actually. We can just make that negative x squared plus 9. But we need our limits of integration. We want to know at what x we're starting with these rectangles. We're going to add them up from what x to what x. We know we want to add them up from here to here. Kids at home, from here to here, from the smallest x to the greatest x. But how do you find out what x is there? Yeah. Yeah, you could set their y coordinates equal to each other, right, to find out where they intersect. So this one we can find points of intersection by hand. We'll set what, because when they intersect, their y's are equal. So y on 1 equals negative x squared plus 4. Y on the other graph equals negative 5. So when they intersect, those y's must be the same. So we set them equal. And if you move stuff around, tell me what you get for x. Oh, I'm so glad you said plus or minus. I'm so glad you said plus or minus. Can't tell you how many times a day. I forget the minus. So, what that's telling us, we okay with the plus or minus 3? That's telling us that the x-coordinate of this point here is negative 3, and the x-coordinate over here is 3. Those are our limits of integration. We want to add up height times width from negative 3 to 3. Now we just got to get our answer. Now it's the easy part. So find the antiderivative. Antiderivative of negative x squared plus 9. There's 1/3. That's here. Plus minus. We plug in the upper, the lower, and we subtract. Negative 1/3 of 3 cubed. Negative 1/3 is 27. Negative 9. Plus 9 times 3. 9. Oh, you're saying 18 is the whole thing, yeah. Okay. Now we plug in the lower limit, the negative 3. So negative 3 cubed is negative 27 times negative 1/3. Positive 9 plus 9 times negative 3 minus 27. So we have negative 9 plus 27, we said was 18, minus negative 18. So plus 18. 36, the area of that enclosed region. Awesome. No. In fact, I'm so glad you just asked that. I just want to show you one where you'd have to go to the calculator even to get the points of intersection. Even if we can't do it all, I just want to do this one on the calculator just to see the setup. Oh man, it's going to be close. Okay, in this one, we've got y equals e to the x. And then you got another sad parabola. Another sad parabola. Oh, you don't have time to color, but I want to. All right, I'll just pick it like a nice, no, sorry, I already picked the yellow. No, yellow is nice. Yellow has a bad rap. On this board, it looks kind of musty and yucky. I know, sorry. I apparently made the class angry with my color choice. Yeah. All right, let's set up the integral. View, full screen. Let's set it up. We want to add up. Now, the graph on top, you can't look outside of the region because y top and y bottom might be different out there. You got to look in here. Which one is y top? Yeah, y equals negative 2x squared plus 4. Negative 2x squared plus 4. Minus y on the bottom graph, which is just e to the x. Width is x. Now, if you have to get you do have to get the limits of integration, you need to know where they intersect. I'm just going to call this A for now, and I'm going to call this B for now, but I want to get them on a calculator. Oh, I don't know. I'm never going to finish this one. But you guys know on the calculator how to get where graphs intersect? Oh, well, they're, it's not ugly. Yeah. You have to go to your calc menu. You got to grasp them both. Oh, look at this. I'm still there. All right. So, the thing that's really neat, though, when you you know how to get the points of intersection. I magic. When you get a point of intersection, you can store it in alpha A and just use like the letter A instead of having to retype it. Second calc, you've done that before? 5. First curve, second curve. I'll show you on one of them how to get it. Guess, you just go over there. When you get an answer, the x coordinate that you want to keep to use later, that negative 1.36, just leave the screen, second mode, and hit store. You're going to store that value in alpha A, enter. Now anytime you use A, it's there. So when you want to put your integral in, you can just, I had to get the other one and put it in B, I can put it in and the answer is 4.675. Woo! Oh, yeah, that is some exciting stuff.